Okay, I suppose we're live here. So I'm Robert Heath. This is lecture number 6 of the Wireless Communications Lab. Let me go over real quick here some of the topics that we're going to cover today. So we're going to start off with the baseband equivalent channel. So what we did in lecture number 5 is we derived the notion of the complex envelope of a passband signal. And so essentially we can write this passband signal as a complex band-limited baseband signal. And so now we're going to look at deriving a similar equivalence if we have a linear time invariant system that connects the passband input to the passband output. So that's what we're doing today. And so you should be able to derive this passband channel and the baseband equivalent and the discrete time equivalent after this lecture. The second topics, and then these other topics we'll cover more quickly, is more about definitions. This is linear complex pulse amplitude modulation. So this is the kind of digital communication signal we're going to consider in the class. And so we're going to go through essentially the definition of it and talk about the parameters, the pulse shape, the symbol period, and essentially introduce notation. So that's not too exciting. And then we're going to talk about constellations, which is, if you remember from like lecture number 2 or 3, is how we map binary information onto points that we end up sending on this complex signal. And then we're talking, in particular here, there's 2 points here. I mean, you should be able to draw the constellation diagram. That's mostly an exercise in plotting. The second thing is you should be able to compute the energy of a constellation and normalize it. And so you also might have to make that constellation zero mean. And this is mostly an exercise that, you get in the homework or an exam. Most constellations that you bump into in the real world have already been suitably normalized. But you should be able to do that. And then depending on how much time we have, and I was looking at when I was printing out the notes today, it's like 10 pages, so it seems like this is too much. But if we get there, we will talk about how to compute the energy, power, and bandwidth of this complex pulse amplitude modulated signal. And it turns out that this is not a derivation as much as a definition because of some weird properties of that signal. And then finally, we'll introduce if time permits, the additive light Gaussian noise channel. So yeah, I think we won't get to this far, but anyways. Okay, so that's the plan here. So let's start off with the baseband equivalent channel. And I'm still using my printer paper from last semester. It's about almost 500 pages that have this marking on it. All right, so lecture number 6 here. Let's see where it went. Over there. All right, so the baseband equivalent channel. So one thing to note here is there's going to be a lot of subtle notation and small differences between some of the things we're defining. So try to pay attention, and I'll try extra hard to write at least the subscripts clearly. So one of the, let me see here. We talked before about this concept of the channel. It's this mathematical model that sits between the input and the output of our communication system. And we've already introduced this notion that in wireless communication systems, we generate a passband signal, maybe that's xp of t. We transmit that, and it arrives at the receiver. And so before we were kind of silent on what happens between when it, gets transmitted and what happens at the receiver here. And what happens in this box here, this is the channel. And from a signal processing perspective, what we want to do is come up with a model for that channel. So we're not necessarily interested in exactly what's happening in the real world. We want to be able to come up with a reasonable model of what's happening in the real world so that we can correct it and remove that distortion from our signal. So there are a lot of different kinds of models. The one you're probably most familiar with is linear time invariant system. That's the one we talk about in our earlier signals and systems classes. But there's linear time varying systems, and there's nonlinear systems, and there's nonlinear time varying systems. A lot of different kinds of channels, and they are useful in different areas of wireless communication. The most common channel model, though, is actually what we've already seen and we're familiar with, which is a linear time invariant system. So let's start this off here by saying, okay, so linear time invariant LTI, it essentially means that the input and output are related by a convolution integral. Now, before I mention that, I want to say one thing here, which is that this is it's not necessarily an accurate characterization of the real world here. Perhaps a better model would be a linear time varying system. And then the linearity is from the propagation medium. So you have signals, reflecting and diffracting, propagating along. And then the time varying because things are moving in the environment. And in wireless, we just generally call that mobility. So it could be transmitter, it could be receiver, it could be reflectors, we're all moving. Now, the reason that we don't use a linear time-varying model is pretty much the same reason we didn't talk about it in 313, our signals and systems class. We didn't talk about it in the DSP class. We didn't talk about it in 445S, because those systems are very hard to deal with. They're hard to characterize. They're hard to estimate. They're hard to equalize. They're generally a pain. And so, being engineers, what we like to do is try to avoid pain when at all possible here. Maybe that's just humans in general. We want to avoid pain. And so what happens is that the system is actually designed so that we can make the linear time invariant assumption. So it's a little bit of a chicken and egg problem here. But let me put that down here. So that we design the parameters, basically select the parameters of the wireless system so the LTI assumption is reasonable. In at least short intervals. And so essentially what this involves is going to be selecting the bandwidth, and with the bandwidth comes the symbol period, and then determining another parameter like the frame length as a function of the maximum amount of mobility you might expect to see. Now, this we will talk about in more detail in probably around lecture number 20. So at this point, it's not important exactly when we say a channel is let's say, time invariant versus time varying. But we'll get to that calculation later when we talk about modeling the propagation channel in more detail here. So with the LTI assumption, what we can do is we can essentially take this input and this output, and we can put in this box here an impulse response, h of tau. And so then we know that the input and output are related by convolution. That's our standard notation here. So let's write that down mathematically here. So with the convolution assumption here, the received passband signal y of t is the convolution between the impulse response h of t, so we put t minus tau here, and then our input passband signal x P is going to be f tau here, d tau. So convolution integral. I'm scared to ask if someone hasn't seen it because I don't want to know that answer. But hopefully everyone has seen it, and if you haven't, maybe come talk to me after class. So the thing is that, as I mentioned, I would try to be extra careful in actually writing cleanly the subscripts. And notice there's no P here. And this is deliberate here. So the input and output are not related by any kind of a band-limited channel. That doesn't make any sense, right? The real environment is whatever it is. You know, there's no little band-limiting filter sitting there in the sky filtering your signal here. So that's the most important thing to note here, is that this is a passband signal. So remember, passband has essentially a signal that lives around some carrier frequency, and otherwise it's 0. And this signal here, I mean, it's not even a baseband signal because it's not even a band-limited signal. It's just some sort of an impulse response. So I'm going to put in particular here, it's not passband. Now, it turns out that, for reasons I'll make clear in a minute here, that we can find another impulse response, and that's what we're going to call the, let's see, this one, yeah, okay, we'll do that as an intermediate step here. So essentially what we're going to do in this lecture here is we're going to find a baseband. This is a complex baseband equivalent channel impulse response H sub E of t. So it's not B, it's actually E, and there's a reason for that. It's not just, you know, me messing with the notation. We're going to find a complex baseband equivalent channel such that we can write a relationship YB of t, that's our baseband signal, is the convolution between our baseband signal, this complex equivalent impulse response, and our baseband input here. So that's essentially what we're going to do right now, is we're going to show how do we connect the H of t here, which is not a passband signal, to something that is some kind of a baseband signal here. So that's effectively what we're going to do right now here. Okay, so perhaps the easiest thing to do first is to show like picture of it. Now, what I have thought about after having taught this class many times is that for some reason I didn't go into art school. I went into engineering, and it may have had to do with that. Can't draw worth a damn. And so I'm trying to now print out my figures here. And what I thought was if I printed the figure out, then I could even squeeze in an example in the lecture, which I know is kind of a novelty here. So this is effectively what we want to do here. So this is it's a spectrum plot. This is frequency. This is our passband X signal and frequency here, right? And remember, this is just an example. Not all signals look like triangles. You know, this is going to be some spectrum here. And the point is that it's 0, you know, signal, 0, signal here. And of course, we expect signal on both sides because of conjugate symmetry. The signal is real. Okay, so the basic idea is as follows here. We are going to send this signal through this channel. And look at this channel here, impulse response. You know, I've just come up with this arbitrarily. It could be, of course, much more complicated than this. Now, what you note here is that this part of the signal here is 0. So this is convolution. So in the frequency domain, we're going to multiply this signal, the frequency domain, by this signal to get this one. So this point-wise multiplication. So all the points here become 0. All the points here become 0. And here and here. And so all we care about from the perspective of the channel is what's happening to our signal here. So actually all we care about is this piece of the signal here. And this argument is a bit similar to when we derived the discrete time equivalent of a continuous time impulse response. You know, there was a similar argument in there that if we band limited it, that's all we care about. So this is the same argument happening here, except we're applying this to a passband signal. Now, what I'm going to do is I'm going to show you the calculations that are going to let us, you know, first of all, compute this and then find that baseband equivalent. And so before showing that, I will summarize the steps of the operations here, again, because it's a little bit easier to see it on this nice computer-drawn figure, which I did draw on the computer, so you know how to use a computer. That's the number here. So, okay, so let's look at this. Yeah, so this is exactly what's going to happen here. So I'm using, it's a different figure, so it's a different channel, but you get the idea here. So here is my carrier frequency. Here is the band-limited part. So notice here, I'm going from HF to H sub P of F. P is for passband. So this is a passband signal. Look right here. Bump, bump, bump. Now the tricky thing here that we have to pay attention to in the derivation is the scaling factor. So I have introduced a scaling factor right here of 1, just as an example, you know, supposing that this point here is 1. So remember from the previous lecture here that, you know, when we go from baseband to passband, there's a factor of 1/2 that comes in. So the spectrum, it goes from, you know, the spectrum's like 1/2 XB, you know, F minus F sub C plus whatever here. So there's a 1/2 in there. But here, look, we're starting off in the passband world, or we didn't start off in baseband. So when we go to the baseband equivalent channel, which is this here, H of B, we pick up a factor of 2 here. And that comes because, you know, when we go from here to here, there's 1/2. So if we start here and go back, there's a factor of 2. Now the problem is that this factor of 2 would multiply our piece of the signal in that band, which we don't want, because that would screw up our signal power calculations. And so then we need to just divide by 2. And so effectively, HE, the equivalent channel, is going to be the complex envelope of this passband signal here divided by 2. So that's essentially all it is here. So that's, and I'll just go through the calculations of that now. Why I'm going to go through the calculations is that I want you to be able to actually compute this spectrum in both the time and the frequency domains. It's useful, really useful for simulation. I mean, a lot of times if you're building like a, you know, LabVIEW or MATLAB or C channel simulator, you will need to use this trick. And this trick is actually surprisingly not well understood by many people in the community, and it leads to incorrect channel model implementation, which leads to, you know, huge issues with the system design team. And I mean, I've seen it again and again, and it's a very, very simple idea. But let's go through that now here. Okay, so that's the plan here. So any questions so far? Maybe on the picture first, because the math will be less clear. You're like hiding over there behind the screen here, out of my line of sight. Okay, well, let's continue here. Okay, so let's look at the, essentially what we're trying to find here. So what we want to do is we want to find this impulse response, H E of t, such that if I had a passband signal Yp of t, and I took the real part of the convolution between He of t and Xb of t, my baseband signal, and upconverted that, so multiplied by this complex exponential, and took the real of that, you know, I would get effectively this relationship here. Should look something like this here. I'm showing you this here for a reason, because we're going to use this trick later. But okay, anyway, so let's start off in the frequency domain here. So in the frequency domain, and actually I think it's a little bit easier to do it in the frequency domain, at least for me. So let's look at, so we have yp of f is equal to h of f xp of f here. Using that same argument as before here, we only care about the portion of h that's within the passband of x. And so we can rewrite this as hp, hp, it's f, where hp of f is the product of a passband filter p of f and h of f here. And so this passband filter, I wanted to go through this here. You can remember some of the Fourier operations here, is going to be equivalent to a rectangle function shifted by this carrier here, scaled by the bandwidth of our signal, plus, and then we have the mirror image of that rect of minus f plus f sub c over w. And because of the symmetry of the rect function, you can equivalently write that as the rect of f minus f sub c over w plus the rect of f plus f sub c over w here. So all I've done here is I've just given you a formula for a filter that has a response that looks like this. This is f sub c, this bandwidth is w, this gain is 1, this is p of f here. So this is just sort of an ideal passband filter here. Now we need this form here and this mathematical form so we can do this in the time domain, find the inverse Fourier transform, instead of just doing hand waving and looking at the picture. Okay, so let's continue on here. Now we just get into computing this HE here. So from here, right here. So this equation here, I can put this in the frequency domain and get a connection between the HE and the HP. So that's like the next step here. What's going on here? So let's do that now. So the objective here is to rewrite yp using now this equation. So let's do that. So 6. Okay, so we can rewrite yp of f, and this comes from the Fourier transform relationship in the last lecture here. That's the 1/2 of what is this in the frequency domain shifted by the carrier plus its mirror image. So we get 1/2. Oh yeah, where's it going here? HE of, let's see, f minus f sub c, x of f minus f sub c plus 1/2 h sub e minus f sub c, and there should be a star here, x and so this right here is equal to this HP of f x p of f here. So this is the product between these two things here. So now we just rewrite this as, so we know the HP of f here is equal to 1/2 HB of f minus f sub c plus 1/2 HB star minus f sub c times 1/2 x sub b f minus f sub c plus 1/2 x sub b minus f minus f sub c here, and then we multiply this out, and notice that these cross terms here are 0 because they're occupying different places in frequency. So we multiply this out, we get 1/4 hb f minus f sub c x sub b f minus f sub c plus 1/4 hb minus f sub c x minus f sub c. And then, so you see right here that, so we have hp of f is equal to 1/4 times this plus its mirror image. And we expect to see 1/2 times this plus its mirror image. So we get 1/2 by letting, so let he of f equal 1/2 hb of f. Then we get this as being equal to 1/2 he of f minus f sub c x b f minus f sub c plus 1/2 he conjugate minus f sub c x sub b star minus f sub c here. Yeah, so, and then and then this is essentially where the 1/2 comes in here. And so we just saw this by more or less just plugging into the equation and looking at these equivalences here. And so effectively what we've done here is we've just calculated, just gone through the steps here of computing this. All right, so questions about this in the frequency domain. Next we'll do it in the time domain. Yes?
How is the baseband equivalent channel helpful to us? What would we benefit by having the equivalent baseband?
Well, that will be, let's see, topic of, I guess it's chapter 5 when we deal with practical impairment. So essentially, if you have a filter that's taking the signal that you're sending to me, and that signal is getting filtered by the propagation environment, to recover the information that's sent, I need to reverse that filtering operation somehow. So if I don't know it, then it's pretty hard to reverse that. So later in the class, we're going to talk a lot about estimating this and equalizing it and correcting for it. And if we don't have a model for it, we can't estimate it and then correct for it later. So, I mean, it's basically just, you know, we want the signal that we're sending. We don't care about the channel. We want to get rid of it, but to get rid of it, we want to know it, understand it, and then we get rid of it. And so having this mathematical model, this piece right here is essentially, you know, going through this whole exercise here, you know, modem, of course, doesn't do this. This is really just connecting propagation theory and channel modeling to DSP. So that's the main reason we do this here. And then, yeah, once we know that this, so now we know that, okay, there's a band-limited impulse response that characterizes the channel between the input and the output of my passband signal. So then all I need to do is learn this. And because it's band-limited, we can sample it and do everything in discrete time. So that was like the end of this piece of the lecture. So other questions? Yeah.
What is the subscript S?
Well, there's no subscript S, so it's all B's. Yep, yep. All that looks like an S. No, that's a B. It's clearly a B. It's right there.
And
there should be a B there too. Yeah, normally I write the X in the frequency domain with the bar on it. Just, I don't know. Normally I just do that. I don't know why. A lot of times I write the H with the bar too, but I didn't do that this time. All right, other questions? Question in the back? Yeah.
On that picture, essentially, going from HCG to switching out and then cobalting.
Yeah.
What's the last step?
Dividing by 2. I mean, this step here is just dividing by 2. Yeah. Any other questions? All right, so actually we're almost done with this piece here, which is the longest part of this lecture. So let's do in the time domain. And this formulation is most useful because, as I mentioned, a lot of times when you're doing performance analysis of a system, you will need to implement a channel model in a simulator, and you'll need to use this form of the model to get the impulse response correct. So in the time domain, essentially, well, I mean, we can go back and look at the operations here and see what it should look like. Because basically what we're doing is we're filtering a signal, we're converting it to baseband. So remember how we converted to baseband? We multiplied by sine and cosine, low-pass filtered, and scaled. And so we can do all of that here. So that's essentially what we're going to do now. So basically, I'll just write this final equation here. So remember, there's a scaling by 1/2 here. That's the 1/2 from our going to the H, from H, B to E. And then there's the scaling of 2, which comes from that, we multiply by sine and cosine. We pick up a 1/2 there that we have to correct for. And this is our low-pass filter. Sorry, I should be writing this in time domain. It's T. Convolving our impulse response, which is convolved with our passband filter in the time domain. And that whole thing here is multiplied by the c to the minus j 2 pi s sub c of t here. So I'm writing the complex equivalent here. So instead of writing the cosine and sine separately, I'm putting them together in the complex exponential here. But this is basically the idea here. So channel filtered by passband, ideal passband filter, converted back to baseband, and that whole thing here, low-pass filtered. And then the things to be careful about here. So if you've done everything correctly here, so first of all, 2's cancel. And second, if you've done everything correctly, when you low-pass filter this signal that's already been passband filtered, that will actually cancel as well. So this, for all practical purposes, goes away here. And yeah, so, but I mean, okay, so I shouldn't take it away here really, because you need it to get rid of this effective carrier here, but it won't show up in the final expression here. But that's essentially the formula here. So low-pass filter convolved with this whole thing right here. And then just as a point of reference here, which might be useful, this P of t, you can show using the Fourier transform identities that this P of t has a form of 2w sine pi wt over pi wt times the cosine of 2 pi f sub c of t. This is just the formula for an ideal passband filter of bandwidth w here. Okay, so yeah, that's it here. And then the final point is that we can derive the discrete time complex baseband equivalent channel, which is h of n, which is just the sampled version t h e of nt here. And then note that you do not need to band limit HE. So no band limiting of HE of t is required because it's already band limited at this point. So before, when we derived this discrete time equivalent, we filtered the channel from first, and then we sampled it. Here we don't need to do that because we've already done that filtering right up here. So that's because of this LW of t that was already in there. Okay, so actually this equation looks perhaps a little strange, but that's it is what it is here. And so now I will go through, just before we take a break, just a the simplest of non-trivial examples that I can think of here. And this is an example that I've given in the past in the homework, and it's in the book as well here. But it's one of my favorite examples, and this is also useful for, when you're talking with like your friends at electromagnetics, talking about propagation and explaining how you get from the real propagation environment to the DSP model. And so we just consider a very simple case where you've got a transmitter and a receiver, and they're separated by a distance of 100 meters. And let's see here. And so we assume that during this distance of 100 meters, the channel attenuates by 0.1. So we receive a tenth of the signal that we sent. And it propagates over 100 meters, so there's a propagation delay. And then we also have, the bandwidth is, so baseband bandwidth is 5 megahertz, and the carrier is 2 gigahertz. Number is all chosen for simplicity of doing the calculation, but relatively realistic. As you've already seen, cellular networks operate often at 1.8, 1.9 gigahertz, and 5 megahertz is the common bandwidth for wideband CDMA. So it's a perfectly reasonable set of numbers here. 100 meters is reasonable distance. Now, the fact that there's not a more complicated channel is another story, but we'll deal with that later in the class. So now let's. So the first thing to do, and this may seem like a stupid exercise, but you'd be surprised how few people can do it. Determine the propagation delay. What is the principle here? If I have 100 meters and I'm transmitting a signal, so how do I compute the delay? Anyone want to throw that out there? Speed of light, yes. Why do we use the speed of light? Yeah, because we're assuming electromagnetic wave here, right? Now, if I said this was underwater and we're using acoustic wave, this would be different. But, unless someone tells you otherwise, we're using electromagnetic wave and we're operating in, some ideal free space here. And so we assume the speed of light is 3 times 10 to the 8th meters per second. We don't need all the precision of, the usual physics type calculation. And then, so to compute the delay, which we call tau sub d for delay, then we're going to take 100 meters divided by 3 times 10 to the 8th meters per second. We get out seconds, which, I couldn't do this calculation in real time, but I have it already pre-done here. It's 1/3 times 10 to minus 6. And then normally we use this engineering notation, so this would become 1/3 of a microsecond. Okay, so with this information here, we know that the propagation channel, it's a delay. It's an attenuation and a delay. So the impulse response is 0.1 delta t minus 1/3 times 10 to the minus 6. So that's our channel. We can plot it. It's an impulse at 1/3 times 10 to the minus 6 t here. So that's all. And so we're going to see that this yields a kind of a non-trivial impulse response from what seems like a very trivial example. And this is the place where so many people get hung up because they say, well, this is delayed, so obviously I just sample this and I'm good to go. So why can't I, by the way, sample h of t directly and create the h of n, the discrete time version? How do you know immediately you cannot sample this? There's a delta function there, and delta basically means this is not band limited. It's going to be flat in frequency. We can only sample band limited signals. Further, just imagine sampling along. It's a delta. You're either going to get nothing or you're going to get infinity if you get unlucky. So, both of those examples, we know we can't sample this directly. Okay, so now let's compute just go through the calculations. So what I'm going to do is I'm going to write down the calculations here, which I have done ahead of time. So hopefully you get the idea here. So first of all, let's compute the HP of t. which is the h of t convolved with the p of t here. This is our passband channel. This is just, an exercise in convolution. So got to convolve that somewhat nasty-looking impulse response with h of tau. Now you appreciate why we only do this for really simple examples. So we plug this in, get 0.1, from the shift property, p of t minus 1/3 times 10 to the minus 6 here. Where p of t is the passband thing I showed you a few pages ago here. And then we could, if we wanted to, we could write that out, and that would be 2 times 0.1 times 10 to the 7. 10 to the 7, where did that come from? That's W, which is the passband bandwidth, which is twice the baseband bandwidth, which is 2 times 5 megahertz, which equals, 10 times 10 to the 6th, which is 10 to the 7th. So that's where 10 to the 7th comes from. And then we have this sinc function here, which is going to be pi 10 to the 7th, t minus 1/3 times 10 to the minus 6. And then we've got, sitting over here, cosine of 2 pi times 2 times 10 to the 9th. That's our carrier frequency, t minus 1/3 times 10 to the minus 6 here. So that's f sub c, and that's t minus tau d here. And so the things to note here, one, we've got this big multiplier here from the bandwidth. We've got the delay incorporated in the sinc function. We've also got the cosine here, which is giving us a frequency-dependent shift, because this is the carrier here. So if there was no carrier, this would disappear, but we have a carrier, so we're going to get a little effect from here. All right, so that's the passband signal. And now I will show you this easy trick. So normally in this case, and of course having done this many times, I know the trick. But what I'm going to do is I'm going to use the formula from one of the previous pages here. That is, if I can find it. Yes. I'm actually going to come back and use this formula here. So I know that the passband signal is the real part of this thing here. Sorry, I know that, no, that's not what I wanted to use. Let's use this here. All right, well, anyways. Basically that, I'm going to write it down here. So the passband signal is the real part of, so remember that factor of 2. So it's going to be, I'm trying to remember the factor of 2 here. It's 1/2. Yeah, so 2 he of t e to the minus j 2 pi f sub c of t here. So this is just the connection between the baseband equivalent and the passband channel. So I'm just doing up conversion plus the factor of 2 that we missed before from that conversion trick there. So actually just using this here, I can look directly and see this here, because this is a cosine multiplying times something. So if I take the real part, basically this means that just by doing this matching here, that he of t is 0.1. So there's a 2 here. It's 2 here. Good to go. Get rid of that 2. 10 to the 7th sinc of pi times 10 to the 7th t minus 1/3 times 10 to the minus 6 here. And then what about this here? What about this cosine here? Well, this cosine corresponds to this piece here, but we've also got this effect of the delay here. And so we could get that by having an e to the minus j 2 pi f sub c of tau here, which is equal to, is 2 times 10 to the 9th times 1/3 times 10 to the minus 6. So that's whatever that is here, 2/3 times 10 to the 3rd here. So this is basically just a little trick that I use mostly because I've seen this before here. But when you have this real thing multiplying a cosine, you can match and figure out that if I have the real part of something times a complex exponential, that's real. And this is how it works here. So this is our complex baseband equivalent channel. So note we have the 0.1, the bandwidth, the sinc function, the time delay, and we have a little phase shift here. The phase is a function of the carrier and the time delay. It's just a phase shift. So the whole thing is rotating in phase. That's all. But it's important that this is where the carrier comes in. So the impulse response, even for a delta function, is still a function of the carrier. Not a strong function, but it's still a function. Okay, so that's the HE of t here. And then just to kind of complete the example here, suppose that we want to get h of n. Well, h of n is t, he of nt. So t, well, sampling at Nyquist. So supposing that we're operating at Nyquist. Nyquist, it's the baseband bandwidth. Yeah, question? Yeah. All right, I think someone messes with this machine every time because usually it's up here. So Nyquist, the signal bandwidth is 5 megahertz. So what would be Nyquist frequency, the sampling frequency? Minimum 10 megahertz. So supposing we sample at Nyquist, t will be equal to, that's 1 over w, the passband bandwidth, which is 1 over 10 megahertz. Right, which is going to be, so this would be 10 times, no, it's 1 over 10 megahertz here. What is that here? 1 megahertz should be, is 10 to the minus 6? Minus 7, yeah, so I'm thinking it's minus 7 too. Okay, so then we just plug that in here, and so then we get, oops, where's my HE of t here? It's over here. Sorry, so we get h of n is equal to 0.1 times 10 to the minus 7 times, ooh, look at that, 10 to the 7 times the sinc, pi, 10 to the 7, nt, so we have n 10 to the minus 7 minus 1/3 times 10 to the minus 6 times, sorry, I put this e to the minus j, and this was 2 pi times 2/3 times 10 to the 3 here. So then this cancels, that cancels. We can multiply through there, and we get 0.1 times the sinc of pi n minus, we're left here with a 10, so minus 10 thirds times pi times e to the minus j, 2 pi times 2/3 times 10 to the 3. So that's the final form here. So look what happened here. So we went from what, in my opinion, was extremely simple in that we had a delta function, time. And what we end up with in discrete time is this. It's not one tap anymore. It's a whole bunch of taps. There's a sinc function here. The time delay shows up right here. If you were really lucky and that time delay was, the sampling period was a function of the delay, then this would be a discrete time delta. But normally it's not. And then this here is a complex phase. So the main point here is that if you want to simulate even a very simple delayed channel, the discrete time baseband equivalent is band limited, and so you're going to get a shifted sinc function in there. And you've got a whole bunch of taps here that are all embedded in there. And this is the piece that is missing in so many references and otherwise, for reasons I know, but I care not to say at this point. All right, any questions on this example here? Yes. Yeah. Yeah. Eight. N. No, this isn't N here.
Is it division? Or just a parenthesis?
Yeah, it's one over there. Yep, I said the subscripts would be clear, but not the parentheses. Nope. Not guarantee that. Yeah. Any other questions on this example here? So what happened if you had two taps in the channel? What if we had two deltas? So this delta we call a tap. So we had another delta. What do you think this final result would look like? Suppose I put another delta over here, 200 meters away. 201, don't care. Well, 201, you would get another sync, right? It'd be another sync, another attenuation, another delay, another phase shift. That's all. So, yeah, and you can do three. So you could have a direct path and a reflection. You could have two reflections, three reflections. You know, you'll have one of these on the homework. I forget which one we gave, but something related to this. All right. Is there final questions on this? All right. So that's it. Okay. So we're running way out of time here. Need to amp up the caffeine clearly here. All right. So I want to take 5 minutes just to ask you all a question here. So I have a new research project that involves cellular systems where phones, in addition to being able to communicate with the base station, can also communicate directly with each other. So you can think about this as being like Wi-Fi direct. But so it's like if you wanted to share big fat video, you could just send it directly without having to go through the cellular system or without having to turn on your Wi-Fi and configure it and all of that here. This is called device-to-device communication. The question I have is, if you had this capability, what would you want to do with it, aside from share big fat files? I mean, because it's probably not that often that I don't know. So I'm just looking for preferably an application that you would use like all the time and that would motivate this as a research problem. I'm not trying to do, yeah. So you want to steal people's information with this technology? Yeah. No. I know what the research issues are. What I want to know is what you would do with this. Like if you had it, like just from the perspective of being a consumer of wireless technology, like what would you want to do with this capability if you had it? I mean, presumably you want this capability, right? Right? I'm going to take a poll here. I hope you want this capability. A lot of cellular companies are spending time, hundreds of engineers working on putting this into the next generation of cellular. So I hope you want it. Someone give me an application here, something you could do with this, something cool, even not cool. Anything. I mean, you put a video camera on your dog, and then you want to, download it at the end of the day. I mean, I don't know. What's the application here? Yeah, but I mean, they have something like that now, so I don't know what this is new here. Yeah. You listen to InfoWars a lot, or? No, okay. Sorry, I was just listening to the radio like last night, and there was an interesting discussion about that, video games.
I mean, that's what it seems like. If you're going to send a lot of information, essentially they're just going to be...
All right, so gaming, yes. All right. Applications that we all have in mind here. Good, glad you confirmed that. Gaming. All right.
If suppose there is some surveillance kind of a system and instead of sending the data over the net, there is direct device-to-device communication and some video recording of the security breach is done, it can be directly transferred to the...
Yeah, so the question here is like, we have a base station here. So it's like, so you could do a lot of the surveillance and stuff like say with Wi-Fi, but why do you need to have a system that that's part of cellular to do this. Like just tell me, like, why do you need cellular in that application? Is it because it's all over a large area, or?
Yeah, probably the range is a factor. Like,
Yeah.
Suppose like I am in Houston and my home automation is the thing which I want to survey is there in Austin. And
Yeah.
So and always internet connection is not possible for such a long range.
Yeah. So the devices at your house would be doing what? They would be talking to each other.
Something like a landline, a phone in your home.
Wow. Yeah.
And it's connected to the devices in your home, and you just call from your mobile there.
Right. But I mean, we can do that with Wi-Fi now. So why? I mean, like, I want something that's like hard to do with Wi-Fi.
That goes your gaming option.
What's that?
There goes your gaming option.
Well, gaming is easy to do with Wi-Fi.
There's not a Wi-Fi that works anyway.
Yeah, but no, okay. The other benefit of this is there's going to be much better performance. So with Wi-Fi, right, if you're downtown, it's too much congestion. If you're trying to do gaming, you might not get a good connection because there's so many access points around. So this will avoid that problem. It'll give you very good quality, very low latency.
It won't give you the same situation for him.
What do you mean?
If you're worried about the access point, the latency, it won't give the same issues for gaming versus his application if you're downtown.
Well, I feel like security is not as delay sensitive, so the fact that the Wi-Fi doesn't work as well is not an issue as much to me. But maybe it is. But I'm not sure that actually the whole point here is so this cellular tower is going to help manage this communication, but the signals won't get sent here and sent back, because if they get sent here and sent back, that congests all of our channels, and we don't get good performance. So, all right, we'll revisit this. One more comment talk here? Yeah.
Isn't there like already protocols for like sharing content, for example? Like if
Yeah.
you're to somebody, I never actually seen anybody use that. But
Right. Well, this is sort of where there's all sorts of near field communication. So a lot of this is used in payment systems, because you actually don't want to use something that can propagate over 100 meters to pay, because then everyone and their brothers will be listening to your signal. Yeah, so there's those contact sharing. There's Wi-Fi Direct. I mean, it's in my phone, but to set it up, it's not like I turn it on and I send you the file. I have to punch in a bunch of stuff. You punch in a bunch of stuff. This would ideally be seamless, just like calling someone. Right, so I could just, let's say, email you a 5 gig file, or just, like instead of texting you, I punch in your number and I punch in the file. And so instead of it, taking an hour to go up here and down there, it would find you, realize you're close, ship it to you right away, assuming you wanted it.
Can it be used for relaying?
Yes, it can be. Why would you want to do relaying? Yeah, people have looked at that. The application here for relaying really is actually emergencies and disaster relief, and so that's the other big area of this is for the cases where this technology presumably will also work if the space station goes down, if it's designed correctly. So it can go into an ad hoc network mode. So. Yes, that could be, yeah, I think medicine too, yeah, yeah, medicine. Well, the company wants to make money. Well, but that's debatable because we don't actually know how often these opportunities happen. I suspect not that often. So yeah, of course, that's what we want. We'd love to save the company money by, hundreds of these operating. Yeah. You have a comment?
Eventually, like if you had a large group of people and everyone is trying to send and receive message instead of using the tower, could they do some way to use all these devices to just hop the information around?
Yeah, and
Yeah.
You can. It's kind of like an ad hoc network, and the problem is that it's very inefficient when you start hopping. So it's actually, and this is one of the reasons, we've done a lot of work here at UT and ad hoc networks and with military applications, for example, and they're so inefficient. Soldiers are much better off, often in combat situations, using cell phones connected to the local cellular company instead of using radios, military radios. It's ridiculous. But that's because those networks, they're so inefficient. So we don't want to do that here, because that's also super inefficient. So we're trying to create a new way to use the existing spectrum. Yes, well. Anyways, but yeah, so fundamentally the problem that we see is just that it seems like this opportunity is maybe not that often. And so we'd like to understand why it could be more often, so that then this would be a sexy application for these companies. Of course, to fund research at UT on this products. Here. Final comment? Anyone? All right. You have a comment? No.
I'm just thinking, maybe if you have an app where you want to find out what's nearby you, would be faster.
Yeah, it could be, but ideally you want to do more. Besides finding someone, then you want to send them some data, because that's the big savings here is is using the fact that someone is close to you for some purpose. Yeah, and so what we're hoping is that so I guess there's also a philosophy that if we build it, they will come. So if we had this, then you all will find something cool to do with it. Yeah.
And what they did was they had the laptops communicate with each other to provide internet, since these laptops would be distributed in an area where, in areas where people live remotely, so there's not always space stations. So what they had was they had the laptops communicate with each other and eventually.
Yeah. So that application is okay because the network is not so dense and there's no option.
Right.
We don't do that here because that's super inefficient.
Right.
But if you've got no infrastructure at all, that's better than nothing. So yeah, and they're looking at that too, but not as much as really just one hop. We don't want to multi-hop it around. Yeah. Okay, all right. This is good stuff here. Someone come back to me with an idea, like a better application. You can start a company on it, whatever. That's fine. I just really we're looking for more motivating examples for this research to justify that there would be a lot of opportunities for this kind of communication. Yes. All right. I suppose I should lecture about something else today. It seems like my long list is not getting covered here. So part 2, linear complex amplitude modulation. And so here I'm essentially just going to define this modulation and the parameters of it. Actually, this will be fast. So the main point here is, we're going to consider a very specific type of digital modulation. Basically, we want to talk about how do we generate that baseband signal, X, B of T. And at this point, I'm going to drop the B because we don't need to distinguish between baseband and passband because everything's basically going to be passband, the baseband now, so we don't need anything here. So we're going to look at this form of modulation that can be represented as follows here. So our baseband signal, X of T, is the square root of EX, the sum over n, minus infinity to infinity, S of n, GTX of T minus n, capital T here. So this is my baseband signal. And then the way that we draw this out, so I guess let me define the different quantities first here. So E of x is transmit energy. And I'll explain more how that relates to the power, hopefully at the end of the lecture here. T is the symbol period. So not the sample period. There will be other times where we'll use like T sub s, and sometimes I use it for a symbol period to distinguish from sample period, or vice versa. But normally I'm just going to use T as symbol period here. 1 over T is the symbol rate. So I should tell you S of n is the complex symbol at time n, discrete time n. S of n will be an element of some set C, which is our constellation. So this calligraphic C for constellation. We talked about this in like lecture 3. These points of this constellation here are called symbols. And then this last quantity here, GTX of T, is the pulse shape. As far as the C here, oh yeah, the M here, M, so this notation here is this cardinality. So the size of this set is M. So there's M symbols. And most of the time, except for just special homework problems, M is some binary power here. So it's going to be some power of 2, where B is the number of bits per constellation symbol. And the way that we draw this out is we're going to have something like bits going into a bit to symbol mapping. Which is input S of n, input of C. It outputs S of n here. And then there's going to be this box that I won't explain today, but I'll explain next Monday here, which is create pulse train. And then there'll be a filtering by the GTX of T, transmit pulse shape, scaling by square root of EX, and producing X of T here. So I forgot to mention the TX here is for transmitter. So there's going to be another G that appears at the receiver. And so this, we'll talk about this, the block diagram we'll talk about more on next Monday. But anyway, so the main thing here is that we are going to generate baseband signals by taking pulses, shifting them in time, and multiplying each of them by a complex number that comes from the symbol. And that's how we create our band-limited baseband waveform. And so the things that we need to talk about, what does this constellation look like? What are the assumptions on the normalization of the constellation? What does this GTX look like? What are the assumptions on its normalization? And that's what we're going to do over the next several lectures, actually. Any questions about this here? Yeah, actually, I was just realizing I didn't need to put it on this lecture yet. But that's kind of what it is. This is supposed to be a little triangle here, like an amplifier. So what we'll talk about in this lecture, to some degree, is some of the assumptions about C, the constellation, and then how we compute bandwidth and power of X of T. And so the other thing to mention here is that this type of digital modulation is actually essentially the most common kind of modulation that's used. And so this applies to a whole host of practical modulation strategies, which we talked about also in Lecture 3. So phase shift keying, quadrature amplitude modulation, etc. here. All right, so now we go to, let's see, talking about the constellation. So the time we have left here, which is almost no time now. I started somehow a half a lecture ahead, and I'm ending a half lecture behind. How did this happen? Doesn't make any sense. It's that example. You see, the examples are trouble. They take up time. It's just, you know, it's examples. All right, constellations. We can do something with constellations here. Yes. All right. So, let me show this first here. So 11. So the constellations. So the constellation is this set here of complex numbers that are specially chosen. And so we'll consider a whole lot of different special cases for this in the class. So it'll be BPSK. The constellation elements will be +1 and -1. And you can see here that m is equal to 2. So you can send one bit of information with BPSK. So you either send a 1 or a -1. We're going to look at 4 QAM, for quadrature amplitude modulation, also known as quadrature phase shift keying. Constellation might look like this: 1 plus j, -1 plus j, 1 minus j, -1 minus j. And then, in general, there's going to be MPAM, where m is a power of 2. And you construct this using essentially equally spaced points. So this would be like m equals 4. So this might be 1, 3, -1, -3. And then there will be the most common one that we'll consider. This is what you'll implement in the lab, is MQAM, where m is a power of 4. And typically you see 4, 16, and 64. This is what's used in 8 to 11, BGA, and AC. It's used in 3GPP, LTE, etc. here. And this is essentially it's like having an m/2 PAM signal and another m/2 PAM signal in real and imaginary. And I'll give an example of this here. So having 16 points. So normally when you plot a constellation plot, you just plot these points here, and then we'll label them with the number. So this might be, that point there might be 3 plus 3j, for example. So we're essentially out of time here. So I'll finish the constellation calculations, but I wanted to show you this labeling here. So remember from Lecture 3 that each of these constellation points is associated with a sequence of bits. And we always, what well, when we think about digital communication systems, we label the constellations with the corresponding bits. So here, if you want to send a 1 in binary, you send 1. If you want to send a 0 in binary, you send a -1. QPSK, 0001, so this is 1J, -1, -J. This is 4QAM. And then this is 16. This is called 8PSK, phase shift keying. This is 64QAM here. The things to note here are that the bit labeling is done in a scientific manner, typically using what's called gray coding. So if you look here, and you can see, barely probably, that there's a 1-bit difference in going from here to here. So there's a 1 introduced right here. There's a 1-bit difference from here to here. And so these labelings are done in a very scientific way. The reason being that the most likely error in a digital communication system is that you mistake this symbol for this symbol. And that we want that to correspond to 1-bit error, not 5-bit errors. So there's something scientific about this. And you'll need this information when you're implementing this, because you'll take the bits and convert them to symbols, and so you'll need to know how the bits map to the symbols here. So what we're going to do, basically just to wrap up here, so what we talked about today was the baseband equivalent channel. And I hope that you can calculate that baseband equivalent for more complicated settings here. And you can use it for simulation. And that's just a concept that's important. It goes beyond the class. Talked about linear pulse amplitude modulation. So here is just basically terminology. This is the signals that we're using. For the next several lectures, we're going to talk about the constellations, how to normalize, and how to determine the optimum pulse shape. Then we're going to talk about the receiver, how to decode the transmitted signals, and so on here. And so that's, I guess, where we're going to stop here. And I will be actually at my office hours today, believe it or not. So see you all there.